Welcome to the Deep Dive, where we cut through the noise to get you well-informed fast.
Glad to be here.
Today, we're diving into something, well, pretty fundamental about human intelligence.
Right. It's not just knowing stuff, is it?
No, it's about connecting the dots, knowing things, and then figuring out new things based on that, drawing conclusions.
Exactly. That ability to reason logically, it's central. And today, we're looking at how artificial intelligence tries to replicate that.
We're talking about building knowledge-based agents, right? AIs that can sort of hold knowledge inside and use it.
That's the idea. AIs that represent information internally and then use that representation to solve problems, to deduce things.
So, okay, how do you even start teaching a machine to think logically? Let's take, maybe a fun example, like from Harry Potter.
Oh, good one. Yeah.
Imagine you have 3 facts.
Yeah.
1, if it didn't rain, then Harry visited Hagrid today.
Okay.
2, Harry visited Hagrid or Dumbledore today, but not both. One or the other.
Got it. Exclusive or...
And 3, Harry visited Dumbledore today.
Right. So as humans, we immediately see it, don't we? If he saw Dumbledore and it was Hagrid or Dumbledore, but not both.
Then he definitely didn't see Hagrid.
Exactly. And if he didn't see Hagrid, well, going back to rule 1, if it didn't rain, he saw Hagrid.
It means it must have rained. It feels so obvious to us.
It does, almost instantaneous. But how do you get a computer to make those leaps, that connection? That's the core question.
Yeah, how does the machine go from those 3 facts to it rained? That's our deep dive.
Okay, so to get an AI there, we need a formal system. Human language is just too fuzzy, too ambiguous.
Right. We need something precise.
We need knowledge representation languages. And the starting point for that is propositional logic.
Propositional logic. Okay. What's the core idea there?
It's all built on propositions. These are just simple statements about the world that are either definitely true or definitely false. No gray areas.
Like, it is raining, either it is or it isn't.
Precisely. And we use propositional symbols to stand for these facts. Usually just letters like P, Q, R.
So P could be it's raining. Q might be Harry visited Hagrid. Simple, true, false building blocks.
Exactly. But simple facts alone aren't enough. We need to combine them. That's where logical connectives come in.
Ah, the glue that holds the logic together.
Yep. There are 5 main ones, each with a symbol and a very, very precise definition using something called a truth table.
Okay, let's break them down. First one.
Not symbols like a little hook. It just flips the truth value.
So if P is true, P is false. If P is false, P is true. Simple enough.
Yep. Then you've got and. The symbol is like an upside down V.
And means, well, both things have to be true.
Exactly. PQ is only true if P is true and Q is true. Any other combination, it's false.
Okay.
Next.
Or looks like a regular V. This one means at least one is true.
So PQ is true if P is true.
Yes.
Or if Q is true. Or if both are true.
Yes, that's the key. It's an inclusive OR. Different from how we sometimes use or in everyday chat, which can imply one or the other, but not both. Right. The only way PQ is false is if both P and Q are false.
Perfect. Now, the one that often trips people up, implication. If P, then Q, symbol's an arrow.
Okay, PQ. This one feels less intuitive sometimes.
It can seem that way. It basically means if P is true, then Q must also be true for the implication to hold.
So the only time it's false is if P is true, but Q is false.
Exactly. Think of it like a promise. If it rains, P, I'll bring an umbrella.
Yeah.
If it rains, P is true, and I don't bring an umbrella, Q is false. Then I broke my promise, the implication is false.
And if it doesn't rain, P is false. Then it doesn't matter if I bring an umbrella or not. The promise wasn't broken either way.
Correct. If P is false, the implication PQ is considered true regardless of Q's value. The condition wasn't met, so the rule wasn't violated.
Okay, that helps clarify it. And the last one?
Biconditional. A double arrow. P if in only if Q.
Meaning they have to match.
Exactly. PQ is true only if P and Q have the same truth value, both true or both false. It's like implication going both ways.
Like, I'll go to the party if and only if you go. Means if you go, I go, and if I go, you go, we're linked.
Precisely. And the beauty is, these definitions, especially laid out in truth tables, are rock solid. Computers thrive on this kind of lack of ambiguity.
Okay, so we have the language propositional logic. How does an AI actually use it? How does it know what's true?
That brings us to the idea of a model. Think of a model as like one specific possible state of the universe, according to our symbols.
The possible world.
Exactly. A model assigns a truth value, true or false, to every single propositional symbol we're using.
So if P is raining and Q is Tuesday, One model could be P true, Q false. Raining, but not Tuesday.
Perfect. And another model would be P false, Q true, not raining, but it is Tuesday.
And P true, Q true. P false, Q false.
You got it. For n symbols, there are 2 to the power of n possible models.
Whoa, okay, so that number grows fast. If you have, say, 10 symbols, that's 210 over 1,000 possible worlds.
Exactly. And with 20 symbols, it's over 1,000,000. This exponential growth is a huge challenge in AI.
So where does the AI's actual knowledge fit in?
That's the knowledge base, or KB. It's simply the set of logical sentences written using those symbols and connectives that the AI is told are true. That's its starting point.
The facts it's been given.
Right. And the whole goal of the AI's reasoning is usually to figure out entailment. We write it as OU bay.
Alpha entails beta.
Ah.
What does that mean, precisely?
It means, does my knowledge base, alpha, logically guarantee the truth of some query beta?
Guarantee how?
It means that in every single possible model, every possible world where everything in the knowledge base alpha is true, the query beta must also be true in that world. No exceptions.
Okay, so if my KB says it's Tuesday and it's January, does that entail it's January?
Yes, because any world where it's Tuesday and it's January is true, well, it's January, has to be true in that world too.
Got it. The truth of the first part forces the truth of the second?
That's entailment. Yeah. And the process of figuring that out, of deriving new truths from the KB, is called inference. AIs use inference algorithms to do this.
All right, so how does an AI actually do inference? What's the first method?
Probably the easiest one to understand conceptually is model checking.
Checking the models, like the possible worlds.
Exactly. It's the brute force approach. To see if the KB entails the query, it literally checks every single possible model.
How does that work step by step?
Okay, for each possible model, step 1, check if the entire knowledge base is true in this specific model.
Right. Does this world match all the facts the AI knows?
Yep. If the answer is no, you ignore that model and move to the next one. It's irrelevant.
Okay.
But if the KB is true in this model, then step 2, check if the query is also true in this same model.
Ah, okay. So you only care about the models where your initial facts hold up.
Exactly. And here's the crucial bit. The KB entails the query if and only if, for every single model where the KB was true, the query was also true.
So if you find even one possible world where all your facts are true, but your query turns out to be false,
then there's no entailment. You found a counterexample. The KB doesn't guarantee the query.
Let's try that Harry's Run example. Okay. Symbols. P Tuesday, Q raining, R Harry runs.
Okay.
Knowledge base was 1 P should Q. R, if Tuesday and not raining Harry runs. 2 P, it is Tuesday. 3 Q, it's not raining. And the query was R, does Harry run?
Right, so 3 symbols. P, Q, R. That means 2 to the power of 3.
8 possible models. 8 possible combinations of true-false for P, Q, and R.
So model checking would go through each of those 8. Is P true? Is Q false? Is R true? That's one model. Then check the KB. Is true true? Yes. Is P true? Yes. Is Q true? Yes. Okay, the whole KB is true in this model.
And now check the query. Is R true in this model?
Yes, we said R was true for this model, so for this model, it checks out.
But we need to check all 8.
We do. And you'd find there's actually only one model out of the 8 where the entire KB, all 3 sentences, holds true. That's the model where P is true, Q is false, and R is true.
And in that specific model, is the query R true?
Yes, it is. Since it held true in the only model where the KB was true, we can say the KB entails R.
Harry will go for a run. It works. How does this look in code? Briefly.
Well, you'd typically represent symbols, connectives like not and implication as objects or structures. Then you'd have a function, maybe model check, that systematically generates all 2n truth assignments and evaluates both the KB and the query under each assignment, following the logic we just discussed.
So for the initial Harry Potter rain puzzle, model checking would eventually tell us the query "it rained" it's true.
Yes, it would systematically find that in all worlds matching the initial clues, it must have rained. But there's a huge catch.
The 2 to the n problem again.
Exactly. Model checking is conceptually simple, but it scales terribly. That exponential growth makes it completely impractical, computationally intractable for real-world problems with, hundreds or thousands of facts.
So AI needs smarter ways to reason. Okay, let's pivot. How do we actually take a real-world problem and translate it into this logical language for an AI? That's knowledge engineering, right?
Right. It's the art and science of encoding human knowledge into a formal representation the AI can use. Let's take a game like Clue.
Classic deduction game. Suspects, weapons, rooms.
Perfect for this. First step in knowledge engineering. Define your propositional symbols.
So mustard could mean Colonel Mustard is the murderer. Plum means Professor Plum is the murderer. Kitchen means the crime happened in the kitchen, and so on. True or false for each possibility.
Precisely. Then you encode the basic rules. You know one person did it.
So mustard, plum, scarlet, and ray, at least one of them is true.
Well, actually, you also need rules saying only one. Like, if mustard is true, then plum is false, scarlet is false, etc. But yes, the core constraint is one suspect, one weapon, one room.
And then you add information as you play. If I get dealt the Colonel Mustard card.
You add mustard to your knowledge base. You know he's innocent.
What if someone guesses, say, Miss Scarlet in the library with a wrench, and another player shows them a card to disprove it, but I don't see which card?
Ugh, good one. You don't know which part is wrong, but you know the whole guess isn't right. So you add Scarlet Library Wrench to your KB. At least one of those things must be false.
And the AI just keeps adding these facts?
And uses inference, maybe model checking if it's small enough, or other methods we'll discuss to constantly update what must be true or false. It can deduce the answer systematically.
We saw this with that Hogwarts house puzzle too, right? 4 people, 4 houses.
Yep. Gilderoy, Pomona, Minerva, Horace, Gryffindor, Hufflepuff, Ravenclaw, Slytherin.
Clues like Minerva is in Gryffindor, Pomona is not in Slytherin.
But the tricky part there, using propositional logic, was how many symbols you needed.
Yeah, you mentioned needing symbols like Gilderoy Gryffindor, Gilderoy Hufflepuff, Minerva Gryffindor, one for every single person house combination.
Exactly. It ended up being 4 people times 4 houses equals 16 symbols just for the assignments. Plus you needed lots of rules, like if Minerva Gryffindor is true, then Minerva Hufflepuff is false, Minerva Ravenclaw is false, and so on. And also, if Minerva Gryffindor is true, then Gilderoy Gryffindor is false. It gets cumbersome.
But even with that complicated setup,
the AI, using its inference algorithm, could still crunch through it and find the unique solution. Gilderoy and Ravenclaw, Pomona and Hufflepuff, Minerva and Gryffindor, and Horace and Slytherin.
So it works even for logic puzzles, and you mentioned Mastermind too, representing colors and positions.
Yeah, even games like that can be mapped to propositional logic, using clues to eliminate possibilities until the AI deduces the hidden code. The principle is the same. Formalize the rules and clues, then let the inference algorithm find the entailed solution.
Okay, but given model checking's limits, what other inference algorithms are there? You mentioned rules.
Right. Instead of checking all possible worlds, we can use inference rules. These are like pre-approved logical steps or transformations. Think of them as tools to derive new true sentences directly from existing true sentences.
Like shortcuts for deduction.
Kind of. They typically have premises, what you know, written above a line, and a conclusion, what you can deduce, below it.
It's a common one.
The most famous is probably modus ponens. We touched on it briefly. If you know alpha beta is true, and you know alpha is true,
then you can conclude beta must be true. If rain, then wet. It's raining. Conclusion, it's wet.
Exactly. Very intuitive. Another simple one, an elimination. If you know alpha beta is true,
you can just conclude alpha is true or beta is true independently.
Yep. If Harry is friends with Ron and Hermione, you can certainly conclude Harry is friends with Hermione.
Makes sense. What else?
Double negation elimination. Alpha becomes alpha.
It's not true that I'm not going. Just means I am going.
Right. Then there's implication elimination, which is handy. Alpha eta is logically equivalent to alpha beta.
If rain, then umbrella is the same as either it's not raining or I have an umbrella. Huh.
Okay. It transforms implications into or statements, which is useful. Biconditional elimination just unpacks alpha beta into 2 implications. Alpha beta, essa beta.
The two-way street becomes 2 one-way streets.
Exactly. And then there are De Morgan's laws, which are super important for manipulating negations.
Those sound familiar from logic classes.
Probably.
Yeah.
Alpha beta becomes alpha beta. Negating an AD turns it into an OR of negations.
So it's not true that both A and B happened means either A didn't happen or B didn't happen.
Perfect. And the other way. Alpha beta becomes alpha beta. Negating an OR turns it into an AND of negation.
It's not true that A or B happened means A didn't happen and B didn't happen.
Got it. There's also a distributive law, similar to math, that lets you distribute A and Ds over OR and vice versa. These rules are the toolkit.
So how does an AI use these rules?
This is where it gets really interesting. We can frame theorem proving as a search problem.
Like finding a path in a maze. How?
Think about it. Your initial state is your knowledge base. All the sentences you know are true.
Okay.
Your actions are applying any valid inference rule, like modus ponens and elimination, to the sentences you currently know.
So applying a rule generates a new true sentence.
Exactly. That's your transition model. The new state is your old knowledge plus the newly derived sentence.
And the goal.
The goal state is having the sentence you want to prove appear in your set of known sentences.
Wow. So finding a proof is like finding a sequence of rule applications that leads from the KB to the desired conclusion.
Precisely. You can even think about path cost, maybe as the number of steps in the proof. It shows how fundamental search algorithms are in AI that can navigate physical spaces or logical spaces.
That's a really cool connection. But is searching through rule applications always efficient?
It can be better than model checking, but finding the right sequence of rules can still be hard. That leads us to another very powerful inference method, resolution.
Resolution. Okay. What's the core idea?
It's based on a single, powerful inference rule designed to work efficiently, especially with sentences in a specific format. A basic version is unit resolution.
Unit resolution.
If you have a clause like PQ, remember that's PORQ, and you also know that P is false.
Then Q must be true, right? To make the first statement hold.
Exactly. If Ron's in the hall or Hermione's in the library, and you know Ron's not in the hall, then Hermione must be in the library.
Okay, that makes it.
The generalized resolution rule extends this. If you have two clauses, say P and PR, and notice one has P and the other has P.
Yeah, they conflict on P.
Resolution lets you cancel out those conflicting literals, P and PE, and combine the rest so you get QRR.
Huh. Let's try that. Ron in hall or Hermione in library, and Ron not in hall or Harry sleeping. The Ron parts cancel, leaving Hermione in library or Harry sleeping.
You got it. It simplifies things by resolving contradictions.
Need some terminology here, I think.
Good idea. A literal is just a basic symbol, P, or its negation, P.
Okay.
A clause is a disjunction of literals connected by ORs, like P, A, key, R.
Got it. ORs of literals.
Sometimes resolution creates duplicates, like QRS. Factoring just means cleaning that up to QRAS.
Makes sense. Remove redundancy.
And the really important one, the empty clause. Symbol is often who. This happens when you resolve two clauses that are direct opposites, like resolving P and P.
What's left? Nothing.
Nothing. That empty clause represents a fundamental contradiction. It's always false. Deriving it is key.
Why is it key, and how does resolution use it? Does it need a special format?
Yes, for resolution to work smoothly, we convert sentences into conjunctive normal form, or CNF.
CNF. Okay, what's that?
It means the sentence is structured as a conjunction A&Ds of clauses. And remember, each clause is a disjunction ORs of literals.
So it's clause 1, A and D, clause 2, and E clause 3, where each clause is like literal AOR, literal BOR.
Exactly, like AT, B, D, C, C. That's in CNF. It's a standardized structure.
How do you get regular sentences into CNF? Sounds complicated.
There's a standard recipe. First, eliminate biconditionals. Then eliminate implications using that alpha-beta trick. Then use the Morgan's laws to push all the negations inward so they only apply to single symbols. Finally, use the distributive law to distribute ORs over A and Ds.
Okay, sounds like a process. So if I had PQ.
You'd first eliminate the implication, then use de Morgan's on the negated part, POER. Finally, distribute the A over the A and D, POR. Now it's in CNF, two clauses joined by A and D.
Got it. So once everything's in CNF, how does the resolution algorithm work? You mentioned contradictions.
Right. The resolution algorithm uses proof by contradiction, it's clever, to prove that your KB entails some query alpha. Step 1. Assume the opposite. Assume alpha is true. Temporarily add alpha to your knowledge base.
Okay, assume the thing I'm trying to prove is false.
Yeah.
Why?
Bear with me. Step 2. Convert everything your original KB and the assumed alpha into CNF. Now you have one big list of clauses.
All right. Got my list of clauses, including the negation of what I want to prove.
Step 3. Start applying the resolution rule repeatedly. Take any two clauses from your list that have conflicting literals, like P in one, P in the other, resolve them, and add the resulting new clause back to your list. Keep doing this.
Generating new, smaller clauses based on resolving conflicts. What's the goal?
The goal is to derive the empty clause.
Ah, the contradiction symbol.
Exactly. If, by resolving clauses derived from your KB plus the assumption alpha, you manage to derive the empty clause, it means your set of clauses contains a fundamental contradiction.
And since the original KB was assumed to be true, The contradiction must have come from the one thing I added.
The assumption, alpha. So if assuming alpha leads directly to a contradiction, the empty clause, then that assumption must be false.
Which means alpha itself must be true.
Precisely. Therefore, the KB entails alpha. Proof by contradiction. If you apply resolution exhaustively and never get the empty clause, then the KB doesn't entail alpha.
Let's try that example. KB is ABC. Query is A.
Okay. Step 1. Assume A.
Step 2. Everything's already in C and F clauses. A, B, C, C.
Step 3. Resolve. Let's take B as C and C. The C and C cancel.
Leaving just. Add that to our list.
Now take A, B, and our new clause, B. The B cancel.
And leaving just A. Add that to the list.
And now take our derived A and our initial assumption, A, resolve them.
A and A cancel. Leaving nothing. The empty clause.
Contradiction found. Our assumption A must be false. Therefore, the original KB does entail A.
Wow. That's actually quite elegant. A single rule, a standard format, and a clear goal. Hunt for the contradiction.
It's a very powerful and widely used inference method in AI systems.
Okay, so propositional logic, model checking, inference rules, resolution. These are powerful tools. But you hinted earlier, with the Hogwarts example, that propositional logic itself has limits.
It does. Needing 16 symbols for that simple puzzle shows its weakness. Propositional logic struggles to talk about objects and their relationships in a general way. It treats Minerva Gryffindor as a completely separate fact from Ramona Gryffindor.
It can't see the pattern. Person X belongs to house Y.
Exactly. It lacks the ability to generalize. That's where first-order logic, FOL, comes in. It's much more expressive.
How does FOL fix this?
It introduces new elements. First, constant symbols. These represent specific individual objects in the world.
Like the actual entities. Minerva, Gryffindor, London, this specific table.
Precisely. Then predicate symbols. These represent properties of objects or relations between objects.
Okay, so instead of Minerva Gryffindor, you'd have maybe a predicate person and another house.
Yep. You could say person Minerva is true, house Gryffindor is true, but crucially, you can express relationships. Belongs to Minerva Gryffindor.
Ah, so the predicate belongs to links the constants Minerva and Gryffindor. That seems much cleaner.
Much more flexible and concise. You reuse the belongs to predicate for everyone, just changing the constant.
And do the logical connectives A and D or not T, etc. still work?
Yes. All 5 connectives from propositional logic carry over and work in the same way to combine these richer statements.
But what gives FOL its real power for generalization?
Quantifiers. These let us talk about all objects or some objects without listing them.
Okay, what are they?
First is universal quantification. Symbol is LAX, like an upside-down A. It means for all, or for every.
So how would you use that?
You could write LAX belongs to Ajax, Gryffindor.
Yeah.
Belongs to LAX, Hufflepuff.
Breaking that down, for all things X, if X belongs to Gryffindor, then X does not belong to Hufflepuff. Or just, no, Gryffindor is also a Hufflepuff.
Exactly. It states a general rule about all members of a category. Incredibly powerful.
And the other quantifier?
Existential quantification. Symbol is a backwards E. It means there exists, or for some, or there is at least one.
So X house X belongs to Minerva X would mean?
There exists some X such that X is a house and Minerva belongs to X.
Or more simply, Minerva belongs to some house. You don't have to say which one, just that one exists.
Correct. And you can combine these quantifiers to express really complex ideas very compactly.
Give me an example.
How about X person XY?
Whoa. Okay. For all X, if X is a person then, there exists a Y such that Y is a house and EX belongs to Y.
Right. And what does that mean in plain English?
Every person belongs to a house. Wow, that packs a lot into one formal statement.
It really does. That's the beauty of first-order logic. It allows AI to represent and reason about complex general knowledge about the world much more effectively than propositional logic.
So that's quite a journey we've taken today.
It really is. From the absolute basics of true-false propositions.
Through building complex statements, defining possible worlds.
Exploring algorithms like model checking, seeing its limitations.
Then moving to inference rules, the search connection, and the power of resolution for proving things by contradiction.
And finally, touching on first-order logic, which lets AI express much more general knowledge using objects, relations, and quantifiers.
It really lays the foundation for how we can build AI agents that, in a sense, know things about their environment and can reason logically about them.
Absolutely. This formalization of knowledge and the development of these inference algorithms are truly fundamental steps towards creating more intelligent systems.
It's all about taking that human ability to deduce, to connect facts, and making it something a machine can perform systematically.
But everything we've discussed today deals with knowledge that's definitively true or false, black and white.
Yeah, propositional logic and FOL are pretty strict about that. True or false, no in between.
Which leads to a thought. The real world isn't always like that, is it? Things are often uncertain, probable, fuzzy.
Right. We deal with likelihoods, incomplete information, best guesses. How does AI handle that? What happens when logic needs to deal with shades of gray, not just black and white?
That's a whole different fascinating area. Reasoning under uncertainty. It requires different tools, different ways of thinking about knowledge and inference.
Something to chew on. How AI moves beyond pure logic.
Indeed. Join us next time on The Deep Dive as we explore how AI grapples with precisely that, the fascinating world of uncertainty.